Thermodynamics 1, Chapter 4, Lecture 1. The leading objectives for Lecture 1 are to examine the moving boundary work, or what's known as the PDV work, commonly accounted in reciprocating devices such as automobile engines and compressors. Reading assignment is Chapter 4, pages 162 to 168. So first, what we're examining is actually a device that actually can physically move. So here we allow the boundary to move. So in these kinds of devices, the work done by the boundary is given by the integral of PDV, where P is the pressure and V is the differential volume. So for example, if we have a gas under a piston, as the gas expands, the piston can move upward. So the piston is displaced to a certain distance, ds. So the pressure that the gas exerts on the piston is the amount of work that's done. Work in this case can be positive or negative. It's positive for expansion, so in other words, that the piston's moving upward, and it's negative if for compression, where we actually reverse the force and compress the gas. So here, this work is work due to the system. So here, that's what the positive and negative means. So if the gas is actually expanding, the gas is doing work, and the work is positive. If the gas is being compressed, then we're doing work on the gas, and so we treat that as a negative work. Moving boundary work is often represented on a pressure versus specific volume diagram. So for example, if we have a gas under pressure and we apply a temperature like heat, and the gas expands, the piston is going to move to the right and increase its volume. Well, as that happens, the pressure drops and the volume increases. So the total amount of work done is equal to the area under the diagram from 1 to 2. The boundary value work depends on the path taken. So, and it really depends on how you get there. So you can go from state 1 to state 2 on a direct path, or you can go on path A or C. So here, path C has the least amount of work because there's less area under the curve. Path A has the most work. It's the most area under the curve. And so these are some kind of representative examples. You also have the case where, like in an automobile engine, where the process is cyclical. In other words, you go from state 1 to state 2, back to state 1. The net amount of work done is equal to the area between the two curves. So for example, as the piston on a car is compressed, it goes from state 1 to state 2. Well, it takes a amount of work to do that, but and then at point 2, the gas vapor is ignited, and the piston goes back up, so it follows along path from 2 to 1. So in that case, the engine does work. So the difference between the two is the net work that's done by the automobile engine. There's different kinds of ways that pressure can vary with volume. One of the most general cases is what's known as the polytropic process, where C is a constant, V is the volume, and N is an integer. So you can plug this in the integral PDV, and you can actually integrate this. So if you plug in for P, you have CV to the minus N dV, and so this is a standard kind of integral that you can integrate from calculus 1. And so here you get this following terms: the difference in pressure. But you can go back to the original pressure equals CV to the minus N, and you can substitute for C times V2 and then C times V1, and replace them with the product of the pressure times the volume. So this equation is very useful for calculating the work from a polytropic gas expansion. If it's an ideal gas, then there's actually a relationship between the pressure and the volume. That's given by the ideal gas law. So you can substitute PV equals MRT delta T for an ideal gas. There's also a special case when N is equal to 1. In that case, you can't really use this formula or this formula because you'll get a 0 in the denominator. But if you go back to the original definition and plug in CV to the minus 1, you can actually integrate that, and that turns out to be the natural log. So this is what's known as an isothermal process. So if a problem says it's isothermal, be sure to use this equation here. If a problem says it has constant pressure, Well, in that case, P is a constant, so we can move it outside the integral and just integrate dV, which is just the difference in volume. So in these kinds of problems, you really have to pay attention to what the problem says. If the problem says it's a polytropic process and doesn't get any indication that it's an ideal gas, well, then you have to use the top equation here. If it says it's an ideal gas, well, then you can use this equation. If the problem says it's isothermal, then you have to use this equation. And finally, if the problem says it's at a constant pressure, well, then you have to use this equation here. So let's take a look at the problem. So it says a rigid tank contains air at 500 kilopascals at 150 degrees C. As a result of heat transfer to the surroundings, the temperature and pressure inside the tank drop to 65 degrees C and 400 kilopascals, respectively. Determine the boundary work during this process. So first of all, when I read this problem, the initial thing that stands out is it says it's a rigid tank. So a rigid tank is that it can't expand. So therefore, the volume is not going to change. So it doesn't matter the rest of the problem. You can kind of stop reading. It says determine the boundary work. Well, there is none, because if the tank is rigid, it can't expand, and so your formula for the boundary work, which is the integral P dV is 0. So therefore, there is no boundary work. Let's look at example 4.2. It says a frictionless piston cylinder device contains 10-pound mass of steam at 60 psi and 320 degrees Fahrenheit. Heat is now transferred to the steam until the temperature rises to 400 degrees Fahrenheit. If the piston is not attached to the shaft and its mass is constant, determine the work done by the steam during this process. So when you read over this example, it says you have it gives you the mass of steam, it gives you the initial pressure and initial temperature. Heat's transferred and the temperature changes. So here, it's kind of you kind of have to recognize the fact that there's a constant pressure being applied to the steam here by this piston cylinder device. Says its mass is constant. So that's going to apply a constant pressure on top of the gas. So we can actually go back to the original formula. P is constant, so we can pull P outside the integral, and so our equation becomes the following. It's just the pressure times the change in volume. Well, in our tables, we don't have the volume's not given, but we have what's known as specific volume, which is mass times volume. So we can pull the mass out of each one of these terms. The mass is constant, and write this as the following equation. So here, what we have to do is we have to look up and find out what state we're in here. So if we look in the initial state, it's 60 psi, 320 degrees Fahrenheit. So if we go to table A5E, we look up, which is the saturated water table. We look at the pressure, 60 psi. What's the saturation temperature? Well, it's 292.69 degrees Fahrenheit. Well, our initial state is at 320 degrees Fahrenheit. So our temperature is greater than the saturation temperature. So what does that mean? Well, that means we're superheated. So we can't use these values. We can't use this table. So we have to go to the superheated tables. But we first have to go to the saturated water tables to find out what our state is. So if you flip over to the superheated tables, table A6E, we can calculate this because we know what the mass is. It's 10 pounds of mass. We know what the pressure is. It's constant. At 320 degrees Fahrenheit, we can look up what the specific volume is. And the final temperature is 400 degrees Fahrenheit. We can look up what the specific volume is there. So we can actually calculate what these terms are. And this term here, again, is a conversion factor from going from PSI foot cubed to BTU. So we find that it's 96.4 BTUs is the amount of work done in this process. So here's a nice P versus V diagram. It shows the process occurring going from state 1 to state 2. and you can calculate the volume. You can calculate the volume this way as well if you really wanted. Once you knew what these values was, it's the area under this curve. But again, remember you got to add this conversion factor because you got to be in the right units. The right units here are BTUs, so you have to plug on this conversion factor. Let's look at another example, example 4.3. Piston cylinder device initially contains 4.4 cubic meters of air. Okay, so this is air. So got to pay attention at 100 kilopascals and 80 degrees C. The air is now compressed to 0.1 cubic meters in such a way that the temperature remains constant. So temperature remains constant. So that means this is an isothermal process. So we have to remember to use the correct formula here. Determine the work done. So here's shows the initial state, initial specific volume. Well, actually the initial volume is 0.4 cubic meters. Initial pressure, initial temperature. So here shows a PV diagram. So this is an ideal gas at constant temperature here. So we're going to use the formula here that in the book, in this particular problem, he goes through and rederives it, but there's no point. You can just use the formula here. Now, initial pressure, initial volume are given. So we can actually calculate what this is. 100 kilopascals, 0.4 cubic meters, natural log of the difference in volumes here. The one thing you can do is as the book points out, is that since P times V is a constant, you can substitute in for a lot of things here. So for example, you can replace V2 over V1 by P1 over P2, since P1 V1 equals P2 V2. Remember, this is back, if you've had chemistry, this is some of the, ideal gas law equations. The way I kind of remember this, let's see if I can get the pencil working here, and I'll show you what I got. You can look at it as P times V equals a constant. So P1 V1 equals P2 V2. So you can replace any of those terms, with you can replace the V2 over V1 just by solving this equation. So V2 over V1 equals P1 over P2. So you can substitute those values in for what you want, because in this case you're actually given the volume change, so it's very easy to just use volumes. So if you plug those numbers in, you get minus 55.5 kilojoules. Now what does the minus sign mean? Well, go back to a few slides. It means that in this case work is done on the system. It's a work input, since it was a compression process. Okay, let's take a look at another example. You get some really good problems in this particular chapter, so I really encourage you to look at these. Piston cylinder device contains 0.05 cubic meters of gas initially at 200 kilopascals. At this state, a linear spring has a spring constant of 150 kilonewtons per meter, touching the piston but exerting no force on it. Now heat is transferred to the gas, causing the pistons to rise and compress the spring until the volume inside the cylinder doubles. If the cross-sectional area of the piston is 0.5 square meters, determine the final pressure inside the cylinder, the total work done by the gas, and the fraction of the work done against the spring to compress it. So here shows the initial state. This is our spring constant. We apply the heat. Now, spring constant is given by what's known as Hooke's law, which is F equals K times X, where X is the amount of compression. Well, that equation actually is a linear equation, like a straight line, Y equals mx kind of thing. So here, the pressure versus volume is actually going to be linear. It's going to start in our initial state at 0.05 cubic meters at 200 kilopascals, and it's going to expand the volume until you get to 0.1 um, cubic meters, which is what we're told, because we're told the volume inside the cylinder doubles. So that sort of sets the initial state we have here. Now this diagram, we don't know what the final pressure is, but so that's actually an unknown in the problem. But I'll show you how we find the value of 320 in a second. But we know it's linear because that's what the Hooke's law is. F equals kx, which is remember F is proportional to the pressure. So therefore, pressure versus volume is going to be a straight line as well because of the spring. Now, the initial state is, we're given the initial state. We know the volume is doubled, so therefore the volume is 0.1 cubic meters. So how far did the spring compress? Well, we know the area because he told us the area of the piston. It's 0.25 square meters. So we can take divide the area into the change in volume to get to delta x, which is 0.2 meters. That's how far the spring actually was compressed. So knowing Hooke's law, then we know that K is the spring constant times the 0.2 meters. So the force is 30 kilonewtons. So the pressure is force divided by area. So again, we know the area of the piston. So that turns out to be 120 kilopascals. So without the spring, the pressure of the gas would remain constant. However, when the piston's rising, compressing the spring, that's going to add to the pressure, and so it's the original pressure plus 120, which is 320 kilopascals, as the final state. So that's how we know that the final pressure is 320. We actually had to calculate it. Another easy way to find the work done there's actually two methods. One way is to actually calculate the volume under this curve. So here we have a rectangle and a triangle. So the area of the rectangle is this base times height, 0.1 minus 0.05 times 200. And then we can calculate the volume of the area of the triangle, which is 1/2 base times height. So it's 1/2 times this distance times this distance, which is exactly what we have here, 13 kilojoules. So this is work done by the system because, again, this is positive. So part C asks for what was the work done against the spring. Well, the part 1 here in green is the work done by the system. The rectangle is the work done by the system, and the triangle is the work done by the spring. So 1/2 base times height is how you calculate that. So it's 1/2 times the height, 300 minus 200, times the base, which is 0.1 minus 0.05, or 0.05. So you get 3 kilojoules for that. You could also have calculated this volume and just subtracted it from the 13. That would have done so too. The volume of 1 is obviously 10 kilojoules. So if you subtract 13 from 10, you get the 3 kilojoules. That's another way to do it. Okay, so that's the end of lecture 1. I'll see you in lecture 2.